Alright, in this video I'm working through some linear algebra unit 5 quizzes. So this first one here, we're going to start with a figure, and it's going to ask us to write a basis for W, and W is the plane, and the triangle is part of the plane. Okay, cool. So we've got this vector here that's in W, this 2, 1, negative 3 vector. We'll call it A. And it seems like the y-axis is also part of W, so I'll just draw a vector right here and call it B. Okay. If I chose it the right length, I could choose B being, a unit vector, and that might be nice. So I'll say it's on the y-axis, so maybe it's where y is 1 and everything else is 0. Okay. So a basis for W would be 2, 1, negative 3, and 0, 1, 0. Because a basis is a linearly independent spanning set. And so that's, we've got a plane, which is a two-dimensional subspace of R3. So it's going to need two basis vectors to necessarily span it. And those are two vectors that are independent and do span it, so that forms a basis. What is the dimension of W? 2, because it's the number of vectors in the basis. Right? If the basis has too many vectors, then it's not really a basis because it's not linearly independent. It would be linear dependent. And what would the other direction doesn't matter in this case. So write a 3 by 3 matrix A whose column space is W. Okay, well, let's see. If it was a 3 by 3 matrix with independent columns, it would span all of R3. So I think what I'm going to do is I'm going to use the vectors that we've got, 2, 1, negative 3, and 0, 1, 0, and then we're going to need the third one to be dependent on the first two, so maybe I could just add them together. So I could have 2, 2, negative 3. I could have 0, 0, 0. I could have 0, 1, 0. I could copy one of the rows again. I could not one of the rows, one of the columns. I could multiply one of the columns by a constant and then just copy it. There's going to be a lot of different matrices whose column space is W, but they do need to have linearly dependent columns. And now for our next job is to write a 3 by 3 matrix whose row space is B. Okay, well, row space is the span of the rows. It's also the range of the transpose. But I don't think that's a terribly useful way of thinking about it. So write a 3 by 3 matrix whose row space is W. Well, if we had the 2, 1, negative 3 and the 0, 1, 0 as rows, okay, if the rows spanned the same space as the columns of the other one, that would be having a row space of W. And so we could see that if we transposed this matrix A to get B, then that would work for us because the row space is the range of the transpose. But I might also say that I could throw in a row of all zeros here, because just throwing in a row of all zeros wouldn't add me any access to new vectors, right? I'd just be stuck with kind of the span of those rows, and that would be represented by plane W. All right, and then write a 3 by 3 matrix C whose null space is W. Okay, I'm trying to remember exactly. We developed a quick, more finesse technique for this one. Oh, yes, I'm remembering now. So if we determined that the null space of matrix C, I'm going to write this out. If the null space of C is equal to W, and A and B are both vectors in W, that means that A and B are both null space vectors of C. So that would mean that C times A is equal to the 0 vector, and C times B is equal to the 0 vector. And I think A and B were probably poor choices given, I started calling those matrices A and B, but it's all right. All right, so with that, I know that if CA and CB both need to equal 0, then I'm going to just kind of copy some stuff down and zoom in. All right, so I'm going to actually start with CB equaling 0. So if CB is equal to 0, that means C multiplied by the vector 0, 1, 0 is equal to the 0 vector. Okay, and, I'm going to say, suppose C is a matrix it's going to be 3 by 3, so it's going to have 3 columns. I'm going to call each of those columns a vector, C1, C2, and C3. And yeah, it's still in your view. Now, if we take the kind of the column view of matrix multiplication, multiplying matrix C by vector 0, 1, 0 is going to give me 0 of the first column of C, so 0 of C1, plus 1 of the second column, 1 of C2, plus 0 of the third column, equaling the 0 vector, right? Because C times 0, 1, 0 equals the 0 vector. Okay, well, if I actually look at it, I'm like, okay, well, 0 of a column, that's not really contributing anything. And then 0 of that column, oh, look, C2 needs to be the 0 vector. Okay, and that's going to be useful to me. Means I'm part of the way there. Column 2 is the 0 vector. But then I can do the same thing, can apply the same principle to CA, right? And I can say if CA is equal to 0, C times 2, 1, negative 3 is equal to the 0 vector. Then I'll say, okay, well, 2 of C1 plus 1 of C2, but I already know that C2 is the 0 vector, so I'm going to write that in there, minus 3 of C3, that's going to equal 0. And so just as long as 2 of C1, okay, so I'm trying to think of, let's do 6. Maybe I'll do 6, 6, 6 there. And so 12 minus 3 times 4, 4, 4, that would be an example of a C that would work. Okay, but it wouldn't have to be like that. It could be 3, 3, 3, and 2, 2, 2. Or it could be, like something else altogether. Like 12, 0, and 1 there. But then we would need to make sure, okay, 2 of C1, that would be 24 minus 3 eighths is 0. Okay, I guess that would need to be also a 0 there. And then 2 minus 3 times 2/3, I think, would equal 0. Let me think about that. Yeah. No. Yes, that's right. Okay, so that's another example of a C whose null space would be W. All right, this next one is let M be the 3 by 4 matrix M here. Write a basis for the range of M. So this is where we're going to use the 2 range tricks. So I'm going to use first range trick 1. And that's where we're going to row reduce. I'll do that now. Add the first row to the second. I think this one should be pretty quick. That'll be a 0, 0, and 3. Negative 1, 2, negative 1, 0, 0, 0, 3. Okay, yeah, and then I'm going to further reduce by, subtracting row 3 minus row 2, getting that 0 there, dividing row 2 by 3, using that entry to clear out the rest of the column, and then I'll be done. Okay, so then I'll have pivots here and there. Okay, so I guess step 1 is row reduce. Then step 2 is identify pivots. Okay, then step 3 is we backtrack to the original matrix and look at the columns that correspond to the pivots in reduced row echelon form. So that's those two. And then basically we're going to report pivot columns. And that'll form a basis for the range. So that would be 1, -1, and 0, along with -1, 4, and 3. And then writing a different basis for the range of M is, I call that range trick 2. That's where we're going to utilize the trick about the row space of a matrix being equivalent to its non-zero rows in reduced row echelon form. So we do that, okay, but we're interested in the column space of M. Okay, but the column space of M is equivalent to the row space of M transpose. So we're going to find the row space of M transpose. Let's see, I'm going to need to zoom out and kind of copy down for M transpose. Transpose equals 1, -1, 2, -1, 1, -2, and 4, and then 0, 0, 0, 3. All right, so if I'm going to reduce this thing and try to find, the non-zero rows it's got in reduced row echelon form, I'm going to say, all right, well, first thing is add the first row to the second row. So bring me a row of zeros. Then maybe I will subtract 2 of row 1 from row 3, and that's going to give me another row of zeros. Maybe I'll add row 1 to row 3, and I'll get 0, 3, 3. Okay, and then I might, divide row 4 by 3 now to make that a 0, 1, 1. And then I'm going to use the fact, okay, like we said, that the row space of a matrix is, there's a basis for the row space in the non-zero rows of the reduced row echelon form of the matrix. All right, so rows, and so I'm going to say, I might actually write this out. Basis for the row space of a matrix, the non-zero rows of the reduced row echelon form. So my basis for the row space of M transpose is going to be non-zero rows, so that'd be 1, -1, 0. 0, 1, 1. And the row space of M transpose is the column space of M. So I could just say that the basis for the range of M is going to be that thing right there, because the range of M is the row space of M transpose. Okay, and that's a different one than I had exhibited up above. All right, next it wants me to write a basis for the null space of this matrix. What I'm going to do is I'm just going to go and grab the original reduced row echelon form and just work with that. So I'm going to just say, okay, this thing can come with me. And so we want the null space, so we're looking at this. Okay, we don't need that anymore. All right, so M row reduces to this. So I think, yeah, and this is as far as I can take it. So I'm going to have x1 minus x2 plus 2x3 equaling 0 and x4 definitely equaling 0. So I think x2 and x3 are going to be my free variables, and x1 is going to be dependent. So it will be x1 equals x2 minus 2x3, x2, x3, x4 has to be 0. and that. So I'm going to, kind of work on factoring this thing. So I'm going to say x2 multiplied by 1,1,0,0 plus x3 multiplied by negative 2,0,1,0. And then, okay, that's my null space right there, and those two vectors form a basis for it. Okay, so the basis for the null space of M would be 1,1,0,0 and negative 2,0,1,0. And then a basis for the row space of M. Again, I'm going to want to use this reduced form here, and I'll say that the non-zero rows in reduced row echelon form a basis for the row space. And I'm just, when I write a basis over here, I'm just writing these, as vectors. So I'm writing them as columns so that they don't, take up the whole width of the screen. So 1, negative 1, 2, and 0. And 0,0,0,1. Okay, and that's going to be a basis for the row space of M. All right, I looked through form Q, and there were not any problems that were materially different, so I think I'm just going to skip on to quiz 5.2, which is about rank and nullity. Okay, so no calculator for these, and we're going to start by giving an example of a 2x2 matrix with rank 0, rank 1, and rank 2. Okay, that'll be a good idea. It's probably a good exercise. All right, rank 0, remember rank is the number of pivots. Okay, so the only way that we could get this is if this was the 0 matrix. Okay, and rank 0 would mean that the rank also is the dimension of the range. So if the range had 0 dimension, that would mean that the range was only the 0 vector, and the only way that we could have a matrix, the only combination of the columns was the 0 vector would be if all the columns were the 0 vector. And so rank 1 would be one where we had one pivot. So what that basically ends up being for a 2x2 matrix is, we've got some starting vector, like say 5 and 2. And the second one is going to have to be dependent. And if we only have 2 and they're dependent, then there's going to be some sort of constant multiplier like 10 and 4, or negative 20 and negative 8, or something like that. So that would be an example of a 2x2 matrix with rank 1, but also maybe an easier one would be to say, okay, it's just going to have one pivot, so that would be one with rank 1. And then a 2x2 with rank 2, that's like full rank, and that would be, an identity would be definitely an example of a rank 2 matrix that's 2x2, but really any sort of matrix that it doesn't have dependent columns, that's any sort of non-singular matrix that's 2x2, anything where AD minus BC was non-zero, that would also have rank 2. Okay. Over here, the nullity of the 8x8 checkerboard matrix shown below. Okay, so what we decided in class was that we were best off thinking about if we were to reduce this thing, what would happen, if we were to put this thing in reduced row echelon form. So if I was to reduce it, I would have, I'm going to just kind of label these two rows. Okay, I'm going to call this one row 1. I'm going to call this one row 2. And notice there's really just a bunch of copies of row 1 and row 2 in this matrix. It's just row 1, row 2, row 1, row 2, row 1, row 2, row 1, row 2. So, okay, if I was to row reduce the thing, I would be left with a row 1, as a row vector, a row 2 as a row vector, and then a bunch of 0 vectors. Actually, what is it, 8x8, so that would be 6 of them, all the way down. Okay, which means that I would have, looking at the rows themselves, I would have 2 pivots. It would be right here and right there. Okay, and then if everything else was 0 below it, that would be, that would be my 2 pivots. So I know that the rank of this thing is equal to 2. because rank is number of pivots. It's also the dimension of the range. It just depends on what perspective you start with as to what definition is going to be useful to you. Okay, if we want the nullity, we're going to have to use the rank nullity theorem. So remember that the rank nullity theorem, I'm going to just kind of put that in. And that's that rank plus nullity is equal to the number of columns in the matrix. So I know that over here, rank is 2 plus the nullity is going to equal 8. Because there's 8 columns in this matrix, that means nullity is equal to 6. And then they might ask us, what is the rank of the chessboard matrix C? And give a reason for our answer. And I think it was pointed out to me that maybe this isn't like actually accurate to chess, but this was made for a better linear algebra question here with the way it was laid out. So over here, again, we have 2 unique rows. Okay, so I think that means that the rank is going to be 2. I'm trying to see if there's anything different about this one. I think I just like brought it in because of, yeah, number 4 is an interesting question. And then also, yeah, to switch it up for the 2 forms. So, okay, the rank's going to be 2 kind of for the same reason. I might call the bottom row the P row, and then the other one the R row. But I could point out that C row reduces into a matrix that just has, pardon me. No, it's going to be, you can take it farther than this, as opposed to the other one where you couldn't. But C is going to go first down to the R row, then the P row, and a bunch of 0 rows underneath that. Now, I'm saying that, where P, R, N, B, Q, and K are all different real numbers, I'm sure there might be a situation, oh no, if R is not equal to N, then we'll have a non-zero determinant right there. And you do know about determinant of 2 by 2. I don't know if you've quite connected that that's what needs to happen there, but anyway, I'll get back to that in a second. Okay, it's going to continue row reducing. Now, I do know that because R and N are different numbers, I would divide, the R row by this lowercase r number right here. To get 1, subtract P copies of the row here, I would not get a 0 there because R and N are different numbers. And so, okay, yeah, I see how this is going to actually definitely have this possibility, and then all of these 0 rows underneath it again. I don't know what's going to come to the right of this, but I do know that's going to happen. And if all the rest of them are all zeros, though, I'll know that the rank is going to be 2 because of those 2 pivots right there. Okay, what is the nullity of C transpose? Okay, well, if I know that the rank of C is 2 and C is an 8 by 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it's an 8 by 8. Okay, so that means that the nullity of C, I guess the nullity of C is not exactly going to be relevant right here. Pardon me. Okay, so yeah, rethink that. Okay, yeah, the fact that you need to be remembering right here is that the rank of a matrix and the rank of its transpose are always going to be equal for every matrix. Oops. Rank of a matrix A is always equal to rank of A transpose. So, as a result, based on the result of number 3, I can say that the rank of C transpose is 2. And I don't need to worry about that, about actually finding the row reduced version of C transpose. That's not going to be. Maybe it's not gonna be. Maybe you could figure it out, but I don't think I want to get into that right now. Okay, and using rank nullity on C transpose, which is also an 8 by 8 matrix, I'm gonna say, okay, now I know that the nullity of C transpose is equal to 6. Now, writing a basis for the null space of C transpose, that was a little bit tricky for a lot of y'all when we did this quiz in class. But since then, we've talked about the idea of a left null space. And I'm just going to get right back into that, and I'm going to solve this problem that way. All right, so I'm going to just kind of start from scratch here in case you just like never really caught from the beginning what I was saying about the left null space or the null space of the transpose. So I'm going to take this, and suppose we're not, but we're going to go back to the chessboard or checkerboard or whatever we're dealing with here. But suppose I was dealing with a matrix that was 3 by 3. Pardon me, I didn't mean to do that. C is a matrix, and it's going to have 3 columns. Column 1, column 2, and column 3. Okay. The null space is all of the combinations, the null space of C is the combinations of the columns that give the 0 vector. Okay. Now let me think about what is C transpose. Okay, C transpose is where we take all the rows and make them columns, or take all of the columns and make them rows. Okay. So if we start to think about the null space of C transpose, we kind of realize that's going to be the combinations of C's rows that would produce, back in the original matrix C world, a row of all zeros, right? It's going to be, a column of zeros in the transpose world. But if we also, we haven't really had much reason to do this, but if we thought about C being still a 3 by 3 matrix here, maybe I'll even, put in some entries. We could be multiplying this. Scoot this up a little bit. If this is a 3 by 3, we could be multiplying this by a 1 by 3. That was a plus. By a 1 by 3 and getting 1 by 3 back. And think about a 1 by 3 would be 1 row, 3 columns. I mean, multiplication of a matrix on the left by a row vector like that is going to be a combination of the columns in the same way that multiplying by a column on the right is a combination of the columns. So if we are thinking about, null space of the transpose being combinations of the original matrices, or the rows of the original matrix, then that's where the left null space terminology comes in, because that multiplication's on the left. So now back to the original task at hand. I need to find a basis for the null space of C transpose. And what I'm going to do is I'm going to think about all of the ways that I could combine the rows of C to get a 0 row. All the non-trivial ways. All right, and so if I'm looking at it, I'm going to continue to use that R and P terminology. I could take, the only thing I can't do is take 0 of all of them. So if I took 1 of the third row, and maybe I'll call that, I'm going to actually call it row 3. Yeah, I'm going to just kind of do a little list. So I'm going to say 0 of the first row, 0 of the second column, talking about rows, 1 of row 3, none of the rest of the rows, 4, 5, 6, 7, 8. Okay, so that's going to be a combination of the rows of C that will give me a 0 row. So I'm going to actually write that out there. 3, 4, 5, 6, 7, 8. Okay, I could take 1 of the 4th row and none of the rest of them, right? Okay, so that would be like that. Okay, then I could keep doing the same thing, right? I could just take 1 of each of these 0 rows, is that the 5th row? So there'd be a 1 in the 5th spot. And then there was another 0 row, so it's going to be another one of these combinations. But then there's a couple of more ways that I can combine this. Okay, I can say, right, yeah, I could take 1 of the P row and then -1 of this other P row. Okay? So I would have 0, 1, 0, 0, 0, 0, negative 1, 0. And then I could also have an R row and then negative 1 of the other R row. And so I'd have a 1 here, a 1 there, and a bunch of zeros. And you can't even see that. Okay, but here it is. All right, now if I go back in and I was to get rid of these kind of commas here, so I just wanted to give you the idea at the beginning that I was just taking how many of each row. I wrote these this way. Also kind of making a point here. Wrote these as row vectors, like you might feel like they need to be if they're left null space vectors or something. See how this would be like nearly impossible to write as a basis, writing them side by side because of the way, in English we tend to write like left to right. Okay, we'd have to stack them up on top of each other, and that kind of looks weird. And that's why oftentimes with these row space situations, I'm writing the vectors as columns, even though I know they're really rows. Because look at that, it doesn't really look all that right. Whereas I could have just turned this sideways, written these all as column vectors, and it would have been like a lot more sensible to you. So pretty much like that. And that's how you would see me write this in the future. Also, I do want to point out, yeah, right, that the nullity of the transpose is 6, so I would expect 6 vectors in a basis, and that is exactly the number of vectors that I do have in that basis. And because that's all the different ways that I could have combined the original rows of C to get the 0 row. All right. Now, okay, on the back, I think these were a little bit more procedural. Find the dimension, the dimension of the column space, that's just the rank. And so we're just going to row reduce here. We're going to subtract 3 copies of row 1 from row 2. We're going to get 1, 0, 2, 0, 4, 0. Oh, okay. So I have just the one pivot here. Rank is the number of pivots, so rank of A equals 1. Find the dimension of the row space of A. The dimension of the row space, well, a basis for the row space of A would be 1, 2, 4. It's the non-zero rows in reduced row echelon form. So on that hand, you could say that. We could also say the dimension of the row space is the rank of the transpose. And we were saying just earlier that the rank of the transpose is equal to the rank of the original, which is going to be 2. Writing a basis for the row space. Oh, I didn't realize I needed to write a basis for the column space of A. Okay, my preferred technique is range trick 1. Just, backtrack to the original column that got you that pivot. And so I'm going to say my basis for the column space is equal to the vector 1, 3. But if you look at the other two vectors, or the other two columns in matrix A, they are multiples of 1, 3, right? And if you think about combining the columns, you're just going to all have, you're going to have a bunch of vectors where the second component is 3 times the first component. That's a line in the xy plane that goes through the origin. Okay, so find the dimension of the row space, write a basis for the row space. Okay, the row space of A is going to be, a subspace of R3. It's going to be, this basis is, so basis for the row space is going to be 1, 2, and 4. And again, just like I was saying on the last page, I'm not going to be writing these as row vectors just because it's not the best way to write a vector. All right, find the dimension of the null space. Okay, we're going to need to use the rank nullity theorem, but we already found the rank was 1, so if the rank of A is 1, and A has 3 columns, okay, then that means the nullity of A is going to have to be 2. And if I want a basis for the null space of A, I don't really have a fast trick for that one. I'm just going to go put in the work, look at the reduced row echelon form over here and say, all right, that means x1 plus 2x2 plus 4x3 needs to equal 0. X1 equals negative 2x2 minus 4x3. X2 and x3 can equal whatever they want. Okay, so I would say that my, basis for the null space is going to be, okay, factoring out the x2, I would have -2, 1, and 0. Then factoring out the x3, I would have -4, 0, and 1. I kind of already did that process all the way through once in this video, so I can do it a little faster this time. Okay, find the dimension of the null space of A transpose. Write a basis for the null space of A transpose. Okay, think about that. Dimension for the null space of the transpose. Well, the transpose has, let's think about this. A is 2 rows by 3 columns. That means A transpose is 3 by 2. So it has 2 columns. We already determined that the rank of A transpose is going to equal 1, because the rank of A was 1. And if A transpose has 2 columns, that means the nullity of A transpose is also going to equal 1. So that's the dimension of the null space of A transpose. That's that right there. Okay, writing a basis for the null space, let's see, that would be, it's the left null space. What are the ways that we can combine? Oh yeah, no, there is going to be a fast way because of the niceness of the numbers here. How can I combine the 2 rows, the first row and the second row, to get a 0 row? Well, I think if I took 3 of the first and -1 of the second, I'd have a 0 row. And so that means that 3 and -1 will form a basis for the null space of the transpose, the left null space. Now I'm going to, write that basis for the left null space. I'll show you, a more algebraic way, 3 and -1. But we will be able to get that the same. All right. So what I'm going to do, I'm just going to get A transpose. Notice I didn't ever have to do that before this. Okay, and I wouldn't have if I just kind of used that row perspective on the transpose. But if you wanted to just make sure 1, 2, 4, and 3, 6, 12, you can go back in 1, 2, 4, 3, 6, 12. That's A transpose. We would row reduce it. We would get 1, 3, 0, 0, 0, 0. So if we were interested in the solutions to A transpose times x equals 0, we'd be looking for situations where x1 plus 3x2 was equal to 0. It's where x1 is equal to -3 of x2, and x2 can be whatever it wants. So this would be like, x2 multiplied by the vector -3 and +1. And so, okay, if you get the basis -3, 1, that's no different from getting a basis of 3 and -1. Yeah, it's one vector. It's where the second vector is -1/3 of the first. Okay, so that's our basis for the left null space, or the basis for the null space of A transpose. Okay, I think I remember that there was a little bit of difference here. This is, this front side is no different from the back side of the quiz I just did. It's exactly the same. This is still the same. Nullity of the chessboard matrix is going to be 6 because the rank is 2. Rank of the checkerboard, yeah, I forgot to erase that in here, so I can just partially cover that up. Rank of the checkerboard matrix is going to be 2. Nullity of C transpose. Oh, basis for the null space of C transpose. Okay, yeah, let's do a basis for the left null space of C. Yeah, let's do that. So we would need all of the different ways that we could combine the rows of C to get a 0 row. So notice that there's kind of just like 2 different types of row. There's going to be, maybe I'll call them like an A row and a B row. So I'm going to just call them A, B, A, B, A, B, A, B. All right, so if I took just any of the A rows and subtracted one minus the other, that would be, that would give me a 0 row. So I could have 1, 0, negative 1 from the first and the third. Okay, I could also have the first two B's canceling each other off. 0, 1, 0, negative 1. I don't think I had 3, 4, 5, 6, 7. This is an 8 by 8 matrix. Excuse me. Had some stuff going on there. And then, okay, I'm trying to see, okay, so I've already done the first two. Like the Okay, so I already did, like those two. So maybe I would need those now. Okay, so 1, 0, 0, 0, negative 1. And I could do the same thing with the corresponding B's right there, right? So I could say that would be the second and the sixth. Okay, so that's 4. Do I need 2 more? So yeah, that would be the first and the last. And now the fact that I don't have to do like the the second with the third or the third with the last, because I've already done with first with all those. See how that might be a little bit confusing. I'm kind of struggling to explain it myself, but I can see that it's not necessary. It would be redundant. Okay, so now I need. Okay, so the first with the last, so it would be first and seventh. 2, 3, 4, 5, 6, 7, 8. Then second and eighth. 1, 2, 3, 4, 5, 6. Oh, whoops, one too many. All right, so that's a basis for the null space of C transpose. The nullity of C transpose is going to be 6 for the same reason. The rank of C transpose is going to be 2 because the rank of C is 2. C transpose is also 8 by 8, so that means the nullity of C transpose is 6. I feel like my explanation of this one wasn't the best. I'm trying to remember. I know I spent more time working with people on the chess one than the checkers on this particular number 4 in class. I feel like I had something better to say about like why we just kind of like always stuck with the first row of, or the first time that A and B showed up, and then kind of subtracted each of the subsequent ones. I don't know, maybe it's obvious to you, but it doesn't seem all that trivial to me. Okay, and 5, 6, 3, and 4. I didn't see that I misnumbered those. It's too bad. All right, so orthogonal spaces. This one was particularly challenging for y'all, I think. So no calculator was allowed for these questions, and we supposed A was in the row space of M. Explain why A cannot also be in the null space of M. Well, that would be because yeah, I guess as long as M is a non-zero matrix, I think I needed to switch that up, and yeah, M is a non-zero matrix. Because if A was a 0 vector that was in the row space, like it could also be in the null space. Okay, so if A, which is a non-zero vector, if A is a non-zero vector of the row space of a non-zero matrix, it can't also be in the null space of the matrix because those are orthogonal spaces. So what I'm saying is that the row space of M is orthogonal to the null space of M. orthogonal spaces like we saw. Actually, in the big picture diagram, they can only intersect at the zero vector, right? Even if they're planes in a higher dimension or something, they can't have a non-zero vector shared between them. So it can't also be in the null space. So I guess because they're orthogonal spaces, and orthogonal spaces can't share non-zero vectors. Question, need to do a little bit of a reword there. Okay, and then, so here let S be the subspace of R4 spanned by these two vectors. Let S perp be the set of all vectors in R4 that are orthogonal to S. Find a non-zero element of S perp. Show the work that leads to your answer. So all vectors in R4 that are orthogonal to the plane spanned by these two vectors. Okay, well, that would mean that this non-zero element of S perp would have to be orthogonal to both of those vectors individually for it to be orthogonal to the plane spanned by those two vectors. Yeah, totally. So what we need is we just need like some kind of non-zero element of S perp. Well, that's just going to be, I'm going to call it A, B, C, D. So we need to be able to dot that with 1, 2, 2, 3 to get 0. And we also need to be able to dot A, B, C, D with 1, 3, 3, 2 to equal 0. All right, so that's going to just pretty much like bring me down to a system. I'm sure that there is, like I'm going to show you the more general technique of finding, I don't even, if you see, oh, I guess if it's somebody, you could have said, because the middle entries are equal on both of those vectors, you could probably done 0, 1, -1, 0. Yeah, I think that was what I was envisioning. Just somebody looking at it and be like, oh, yeah, I think both of these would be orthogonal to that one. And I think that's going to be pretty obvious in the algebra when I keep going. I am going to keep going because I think that's what was most obvious to some of y'all, was to go over here and say like, all right, A plus 2B plus 2C plus D equals 0. And then A plus 3B plus 3C plus 2D equals 0. And then you could make a decision for like two of the values. You could just be like, okay, I'm going to let A and D both equal 0. Okay, there's going to be some way that it works out, right? Because then it'll be down to a 2x2 system. And then you'd have 2b plus 2c equals 0 and 3b plus 3c equals 0, and one potential solution to that would be -1 and 1 for b and c, respectively. That's how you could get down to that. You could you could continue to not see the forest for the trees and continue to turn this into a matrix and row reduce and find the infinitely many solutions and choose one of them. But I think that would be a bad idea. Right, just try to figure out, a vector that's orthogonal to both of the ones that you were given. So the next one is let P be the plane represented by this equation. And this one, we got a lot of discussion out of this one. Okay, so we are going to find a basis for P perp, the set of all vectors in R3 that are orthogonal to P. I'm going to do this by thinking about the plane itself. Let's see if that works. Yes. All right, that's going to be my plane. Then I'm going to say the origin is going to be right here. Okay. The normal vector to this plane is going to be the vector, or a normal vector is going to be 1, 2, 3. Right? The numbers that we just read off the kind of the slope numbers, what we said at the very beginning of the course. So if I'll label this vector n is equal to 1, 2, 3. Okay, and I told you in class that the only way in R3 that you can have an orthogonal subspace to a plane is by having a line. Is that two planes can't be orthogonal in R3 because R3 doesn't have quite enough dimension. Let me get that to be a straight line real quick. Okay, that's going to be good enough. Got that here. And there we go. All right, but vector n is equal to 1, 2, 3. Well, the orthogonal subspace is the whole line, but a basis for p perp. Okay, so basis for p perp is going to be just vector n. Okay, because it's a line, and a line only has one basis vector because it's one-dimensional. Okay, then we'll find a 2 by 3 matrix M whose null space is P. And, okay, yeah, I think people really overthought this one. But, you think about how you get the null space is you augment something with 0 and row reduce. And then think about what you get back at the end. Like... Right, this might be what you got at the end, right, after row reducing. But then you would say, oh, okay, that means that x1 plus 2x2 plus 3x3. You know what y'all do? You write out the equations and kind of like go through the algebra without thinking about it too much. But you think about x2 and x3 and x1, that's just x, y, and z, right? So, and that's how, we know how we find a null space. We've known that for a long time. So this could just be the 2 by 3 matrix that, if I went and augmented it with 0 and row reduced, well, it's already row reduced for me. That would be perfectly fine, right? We could have 1, 2, 3, 0, 0, 0. We could have 1, 2, 3, and 4, 5, 6 as the second row. We just can't have a second independent row because then it would we'd have a different null space. It would be just as yeah, maybe just a line. I don't know. Then we're going to use the list of vectors here for the next 3 questions. So if S is the span of just X, okay, so 1, 1, 1. Maybe I'll even draw you that. That's my drawing of the vector 1, 1, 1. So that's vector X. Okay, the span is going to be the rest of the line. Let's see if I can make that happen. Okay, as best I could. Ooh. Okay, yeah. It looks all right. This is going to be S. Okay, write a basis for S perp, the set of all vectors in R3 that are orthogonal to S. All right, yeah, that's the best drawing I've got here. It's the plane that's orthogonal to that vector. Okay, but writing a basis for S perp, I'm trying to think, and we did come up with, and I'm kind of delaying showing you the general technique as long as possible, but it might just be an issue of doing it. I don't really want to. I'm trying to think if there's a different way. How did y'all do that? Oh, I know what y'all did, and it was definitely the most obvious thing to do. Okay, so all vectors X that are orthogonal to S, well, whoops, we already have X. All vectors V that are orthogonal to X, well, that means that V dotted with X equals 0. The 0 number. And V is going to be V1, V2, and V3. All right, so that means that V1 times 1 plus V2 times 1 plus V3 times 1, that needs to equal 0. And then we're going to say, all right, well, then I'm going to say that V1 equals negative V2 minus V3, V2 equals whatever it wants, and V3 equals whatever it wants. Then we factor out the V2 and the V3 from this kind of like generalized vector that's starting to appear on the right. of the equal signs there, and I'll say, all right, well, the basis for S perp is going to be, all right, factoring out V2, I have negative 1, 1, and 0. And factoring out V3 would be negative 1, 0, 1. Yeah, I knew that doing this one this way, like a little more algebraically, would be good before I reminded you of the general technique for finding an orthogonal an orthogonal complement. All right, so just to remind you about the orthogonal complement, if you've got a subspace of Rn called W, then W perp, that's that symbol that looks like an upside down T, it's like a perpendicular symbol. W perp is the set of all vectors in Rn that are orthogonal to all of the vectors in subspace W. Okay, so it's an orthogonal subspace, but it's also kind of like the biggest one that exists in the rest of the space. Okay, and then there's a theorem that is, we talked about in class kind of briefly, is that, and I'll just copy it in real quick. It says that if W is the column space of a matrix, then W perp is equal to the null space of the transpose of that matrix. It's the left null space of that matrix. And we actually already knew that the range and the left null space were orthogonal spaces, but this is basically prescribing us a recipe for the orthogonal complement. First, we're going to form this matrix out of a basis for W. Hopefully we've got a basis for this space, or, if we don't, then we're just going to figure out a way to express this space as the column space of a matrix. We're going to compute the left null space, and we'll do that by, like it says, computing the null space of the transpose. So let's just get back to the quiz question and do that. All right, so T is the span of X and Y. So X and Y are probably going to form a basis for T, provided that they're not dependent, and they're not. Okay, they're independent, so they're going to form a basis. Okay, that means that if I want T perp, I'm going to need a thicker pen. T perp is going to be the null space of A transpose, where A has columns given by X and Y. And I'm going to actually copy that in. Okay, I knew X was 1, 1, 1. And Y is 1, 1, negative 1. Okay, so I need to find the null space of A transpose, but that's not too hard, right? I especially got quite a bit of experience doing that. We've got this recipe, so we're going to be able to do this. Okay, so the rows become columns. 1, 1, 1, 1, 1, negative 1. Or columns become rows, however you like it. Okay, now we're going to row reduce this, and we're going to have 1, 0, 1, 0, eventually 0, 1, like that. Okay, the null space of the transpose is going to be x1 plus x2 equaling 0, and then x3 necessarily equaling 0. Right, so that's going to be x1 equals the negative of x2. x2 has to equal, or can be anything at once, and x3 is the thing that has to equal 0. Okay, so if I factor out x2, okay, yeah, and this is going to make sense, I would have the vector negative 1, 1, 0. You can check and see that that one's orthogonal to both x and y. Yeah, totally. And then also, if we think about it, that's going to be a basis for T perp. If we think about it, okay, the span of x and y is going to be a plane in R3, and only a line can be orthogonal to a plane in R3, because there's not enough dimension for two planes to be orthogonal to one another in R3. All right, if U is the span of the 0 vector, write a basis for U perp, the set of all vectors in R3 that are orthogonal to U. Well, the span of 0 is just the 0 vector, and everything's orthogonal to the 0 vector. So I'm going to say, a basis here would just be I and J and K, the easiest one. Because it's all of R3, it's going to be the set of all vectors that are orthogonal to U. All right. So with quiz 5.4, I'm going to give you the projection formula and then the Gram-Schmidt algorithm. We don't really need to do the Gram-Schmidt algorithm on this quiz, but we might need to Actually, I don't think we do. But the algorithm is y1 equals x1, and then yn equals xn minus the projections of xn onto each of the previous y's. So that would be xn onto y1 minus the projection of xn onto y2. It's harder to write than to do, in my opinion. Minus so on until you're out of previous vectors to project onto. Okay, and then so compute the projection of u onto v. That's going to be much easier. We're just going to use that formula. So u onto v. So that's going to be u dotted with v divided by v dotted with v. That's going to be a constant. Okay, and we're going to say, all right, first I'm going to compute that. So u dotted with v is 20 plus 15 is 35. Divided by v dotted with v is going to be 16 plus 9 is 25. So it's going to be 7 over 5. And then we know that we're going to take that number, projection of u onto v is going to equal 7/5 of v. And that's going to be 7/5 of 4 is 28 over 5, and 7/5 of 3 is 21 over 5. All right, sketch the projection of A onto B. Okay, well, what I'm going to do is try to extend B the way it was going. That was not straight enough. Okay, I can do that. I can do a little better than that. That didn't work out so well. That's not really getting the job done. Let me do this a little better. There we go. So if I'm looking for the projection of A onto B, I'd look for, kind of where this is going to come down perpendicularly, and then the projection itself is going to be the vector I'm going to draw right there in blue. I think that's a good enough sketch for our purposes here. Find the length of the projection of Y onto Z. Well, the length of the projection, let me think about that, it's the ratio of the, no, it's the length of the projection is the length of A times cosine of the angle. But it's in there in the, let me do some algebra. So remember, the projection of A onto B is A dotted with B divided by B dotted with B, which is the length of B squared times B. And that's just a constant out there. But it's A dotted with B divided by the length of B times, that's probably a bad times, B over the length of B. If I split out that squared, that's a unit vector, so this is the length. Okay, that's what I would call the length of projection. I guess of A onto B, which is relevant. So Y onto Z. So the projection of Y onto Z, okay, so that's going to be, I'm looking for Y dotted with Z divided by the length of Z, because I'm doing the projection of Y onto Z. Okay, so dot product, that's going to be equal to 2 plus 4 is 6 divided by the length of Z is the square root of 1 plus 4, and 4 is 8 plus 16. Oh, like that. And that's going to be 6 divided by 5. Okay, that'd be nice. Okay, now I'm going to project compute the projection of C onto D. So I'm just going to use the formula. It's going to be C dotted with D divided by D dotted with D. Figure out what that value is. So that's going to be, the dot product of the two is going to be 2 minus 3 minus 6. D dotted with D is going to be 4 plus 9 plus 36. That's 49. Oh, that's, remember, we're not taking a square root. But if we were, it would be nice. So 2 minus 3 is negative 1 minus 6 is negative 7 over 49 is negative 1/7. All right. Then, okay, so the projection of C onto D is going to equal negative 1/7 of D. And that's going to be negative 1/7 of 2, negative 3, and 6. And that would probably be an all right place to stop. But I think we can go all the way 3/7 and negative 6/7. Okay, and then find the projection of x onto the plane spanned by the vectors. This is as close as I'm going to need you to do for Graham-Schmidt. In this class this year, at least in the 23-24 school year, who knows, maybe in a different year I feel differently, but the projection onto the plane is going to be this, right? Whoops. Let me try that a second time. Add that. All right, right there. So this is the projection I'm looking for. Maybe I'll call this W. My eventual, my goal here. Okay, what we know is that when we're doing Graham-Schmidt, we're actually interested in this vector, right? Because that's orthogonal to the plane, but that's not exactly what we're doing. Okay, we're going to be interested in obtaining W by first projecting X. So I guess this is going to be a vector X up here. And then these are the, the vectors spanning the plane, which I'll just call V1 and V2. Oh, okay, and X is still, yeah, it's right there. They're telling us it's that. Oh, negative 1, negative 1, 1. It's a different X. Maybe that was even a different problem or a different quiz. Okay, so here, all right, what am I thinking? Oh, yeah, what I was trying to say was that the projection of X onto V2 should probably come down around, say, about there. Yeah, plus the projection of X onto V1, which should be right there. If I add those two projections together, they should give me W. So I'm going to say first up here, this is going to be the projection of X onto V1. Then down here, I'm going to have the projection of X onto V2. We're going to need to compute those. Okay, so I need projection of X onto V1. Okay, so I'm going to do X dotted with V1. Okay, so that's negative 1, 0. What? Okay, so that's 0. Well, that's a problem. I didn't realize that the x vector I gave you was orthogonal to one of these. Could be a problem. Okay, whoops. It appears that x was already orthogonal to the plane, so its projection is going to be a 0 vector. Okay, that one was kind of messed up. Let me check and see if on the other form it worked out. Yeah, I tend to think that was just a mistake since the same thing did not happen on form Q. All right, so I'm going to do the same idea. I'm not going to be as careful with the drawing. So I'm going to say that's going to be the projection, the first one, projection of X onto the first vector. And it doesn't matter which one I let be the first and the second. I think that was the opposite of how I'd drawn it before, but it's all right. So I'm going to dot X with V1. So I'm going to get negative 1 plus 0 plus negative 1 is negative 2 divided by V1 dotted with itself would be 2 times V1. So that's negative of V1, and that's going to equal, oh, that's weird. But probably it's just that X is pointing the exact opposite direction that it looks like it's pointing in the figure. So negative 1, 0, 1. That's the projection there. And then over here, right there, so right there, that'll be the projection of x onto V2. And I'm going to dot x with the second vector, so it'll be -1 times -1 is 1, minus the 1 is 0, minus 1 is -1. Divided by V2 dotted with itself is going to be 1 plus 1 plus 1 is 3. -1/3 of V2, which is going to equal +1/3, -1/3, and +1/3. I would need to add those two vectors together, these two projections. I would add them together to get the projection of x onto the plane, the thing that I'm eventually hoping to find. So this thing right here is equal to, adding the x's, -1 plus 1/3 is -2/3. -1/3 plus 0 is -1/3, and 1/3 plus 1 is going to be 4/3, and that's the projection of x onto the plane spanned by those two vectors. That was a good example. Okay, is there anything else on these quizzes? No. Okay, that's been a really long video. It's been a lot of linear algebra for today. That's going to be all. Thanks for watching.